Hey everyone. In this lecture, we're going to talk about the idea of arc length. So we want to be able to measure a curve we'll call f of x. The curve y equals f of x may, let's say, look something like this. I'll create some points for us to talk about along the path of this curve. We'll call this p sub 0, this first curve. This curve will be at A. Then there's p sub 1, p sub 2. We have another curve, another point, and another point there, another point there, another point, and then a final point there. Okay, we'll call this p sub k, so this will be p sub k minus 1. And maybe this last point, we'll just identify this one as b, so that'll be p sub n. All right, so if we want to find this arc length, the length of this curve, then we can probably go along this polygonal path, right, from point to point. And if we go along this polygonal path, this path where we have p sub 0, p sub 1, p sub 2, and so forth, then that length of that polygonal path approximates the length of the curve y equals f of x, whatever it is, from point A to B. All right, so now to perform the calculation for the length of the curve y equals f of x, let's take a look at the definition that we need. So the definition here tells us if f prime is continuous on the interval a to b, then the length, which is the arc length, of the curve y equals f of x from the point A to point B is the value of the integral, and we'll say L. Most textbooks use L for the arc length. So L is equal to the integral from A to B of the square root of 1 plus f prime of x squared with respect to x. Sometimes it's written alternatively as what's below, the integral from a to b of the square root of 1 plus dy dx squared with respect to x. So this is what we're going to have to follow, and you can use any variation of that. One just has f prime of x, the other one has the Leibniz notation of dy dx. Okay, so let's say we have this curve y equals f of x, and let's name it. It's actually y is equal to 4 times the square root of 2 over 3 x to the 3/2 power minus 1. Okay, so this is our function in red. Y equals 4 times the square root of 2 over 3 times x to the 3/2 power minus 1. All right, so then we want to draw a line segment from A to B. So I'll draw the line segment, and here's A and B. The line segment will look something like that. Okay, so A is at 0, comma, -1, and I'll tell you where B is. B is at 1, comma, 0.89. So we can say that looking at this visually that the length of this curve is slightly larger than the length of the line segment joining points A and B right here. All right, so let's take a look at our example that will relate back to this sketch and diagram. All right, so it says to find the length of the curve shown in the previous diagram, which was right above us, which is the graph of the function y equals 4 times the square root of 2 over 3 times x to the 3/2 power minus 1. And it's from the interval 0 to 1. All right, so let's go ahead and take a look at how we can go ahead and solve this. So we're going to use the equation that we were talking about earlier for arc length and that we had written down. So it was L is equal to the integral from a to b, the square root of 1 plus our dy dx squared with respect to x. All right, so when we're using a is going to be 0, b is going to be 1, right? So now we can go ahead and work through this problem. So let's go ahead and just take this portion over here to the right. So we're going to take that portion, the dy dx, and then square it. So dy dx. So we're going to take the derivative of that portion that I just highlighted. So the derivative of that portion for us is going to be taking the derivative of the 4 square root of 2 over 3, and I'll write that down. So what's y? Y is going to be for us 4 square root of 2 over 3 x to the 3/2 minus 1, right? So we're just using that and taking the derivative of that. Well, as you can see, that 4 square root of 2 over 3, that's a coefficient. So we can move that out to the front according to our differentiation rules that we learned way back. And then just work on this part right here, right? That x to the 3/2 power. So we have 4 square root of 2 over 3. X to the 3/2 power is not a big deal. We're just going to use the power rule. So we take the 3/2 and multiply it or bring it out to the front of the x. And then we're supposed to subtract 1 according to the power rule. So 3/2 minus 1, 1 is like 2/2. So 3/2 minus 2/2 is going to be 1/2. And then minus 1, the derivative of a constant is just 0. Okay, and then we can just clean this up a little bit. Looks like the 3's will cancel out. 2 goes into itself once and into 4 2 times. So that leaves us with 2 square root of 2 x to the 1/2 power. All right, so now we have that dy dx portion, but then what does it say to do? It says square it. It says to square it. So let's go ahead and do that. So let's say we have dy dx, but now we're just going to square it. So to square dy dx, and I'll write it over and say 2 square root of 2 x to the 1/2 power. Right? When you square that, what occurs? Well, you're going to have 2 squared, the square root of 2 squared, x to the 1/2 squared. So the 2 squared is going to be 4, right? The square root of 2 times the square root of 2 is going to be the square root of 4, which is going to be 2. And then x to the 1/2 power raised to the second power. Properties of exponents, when you raise a power to a power, you multiply them. So 1/2 times 2 makes 2 over 2, which is going to be 1. So that's going to be 8x to the first power. All right, now taking a look at this further. So we have the dy dx and we also squared it. So what else is going on? What else is going on? We have to say 1 plus that, what we just did, along with taking the square root of it. And let's not forget, we also are going to integrate as well. So let's take a look at all of that and rewrite what we have. So L is equal to the integral from 0 to 1 the square root of 1 plus, and we just already did the dy dx, and we squared it and got 8x with respect to x. All right, so now we have to integrate the square root of 1 plus 8x. So looks to me we have to think back to our skills and use some u substitution. So let's let u equal the 1 plus 8x. If that's the case, then du is going to be, okay, the derivative of 1 is nothing, is 0. The derivative of 8x is 8. And this is with respect to x. So therefore dx is equal to, dividing both sides by 8 over here to the right, du over 8, or 1/8 du, right? So if that's the case, then we're going to say to ourselves that that square root of 1 plus 8x, that's just like saying 1 plus 8x to the 1/2 power, right? Everywhere we see an x, but that's only one place, so we'll just plug that in. And I'll let you do that scrap work, just a matter of crunching some numbers here. So what you should get is 13 over 6, 13 over 6, right? If you plug in the 0, then 0 times 8x is 0, 1 plus 0, and do all of that you need to do. So then you should get 13 over 6, as I was saying, and that's approximately 2.17. But just to be clear, let's go ahead and go through that to make sure you do know how to get to the 13.6. We don't want to just assume, right? So I'll work that out on the side. Let's say we're plugging in the 1 first, right? Plugging in that 1. So if we plug in 1, first of all, the 2 times 1 is 2, 8 times 3 is 24, so 2 over 24 is 1/12. So we have 1/12, and then plugging in the 1 in for x, 8 times x, or 8 times 1 is just going to be 8, so that's 1 plus 8 to the 3/2 power. Okay, so then that's going to be 9, right? 1/12, 9 to the 3/2 power. 3 over 2, what does that really mean, right? That means the square root of 9, and then it means to cube it, according to the definition that we know from algebra. So 1/12 times the square root of 9 is 3, and then you cube that 3, that's going to be 27. So this is going to be 27 twelfths, which reduces to 9/4, right? 9/4. All right, so I'm going to erase this, and now I'm going to substitute in the 0. All right, I'm going to substitute in the 0. Okay, so now I've erased that. Now I'm going to substitute in 0 for x, but it still holds that we have that 1/12. And then 1 plus 8 times 0 is going to be 0 to the 3/2 power. So we have 1/12 times 1 to the 3/2 power. Well, we just said a few moments ago, 3/2 power means take the square root, and I'll write it out, the square root of 1, and then raise it to the 3rd power, and you still multiply times 1/12. Well, square root of 1 is 1, 1 to the 3rd power is still going to be 1, so that's times 1/12, so we get 1/12. All right, so now if we go back, okay, what do we have? We had 9/4. Oops, sorry about that. We had 9/4, and now we're supposed to subtract it, right? According to the fundamental rule of calculus, we subtract it from inputting that 0, which we then got a 1/12. That's going to be, the LCD will be 12, so we change the 4 into the 12 and multiply the 9 times the 3, it's 27. So minus 1/12. and then that's going to get us 26/12, which is 13/6. So that's how we got that. Just want to make sure we are good with that. Then punch that into a calculator, and then we'll get approximately 2.17. Okay, so looking at this, we got 2.17, right, through our calculations. Let's take a look at it using those points that we were given. So what we were given, if you go back into the video, rewind back, you'll look at the diagram. Point A was 0, -1, and point B was, I think I gave it to us. It was 1, 0.89. 1, 0.89. All right, so if we go ahead and apply this distance formula that we know, x sub 2 minus x1 squared plus y sub 2 minus y sub 1 squared, just plugging those values in. So we get x sub 2 is 1 minus 0 squared plus y sub 2 is 0.89 minus a -1, and then we square it. So we should get 1 squared plus 1.89 squared, and then that gets us 4.5721, which is about 2.14. Right, so notice that the length of the curve is slightly larger than the length of the straight line segment. Right, so we had 2.17, that's larger than the 2.14. The length of the curve is slightly larger than the length of the straight line segment that joined the points A and B on the curve, right? And we had mentioned that earlier when we first began the lecture.